Hello student, today we will learn a very important topic. So it's called Chebyshev inequality. Chebyshev Chebyshev's inequality. Okay, and this is after the Russian mathematician Chebyshev. Okay, so we will first write down the statement, and then I will tell you what is the geometrical meaning, and then the proof. Okay, and then so let us start with the statement. So what does the statement tell? So statement of the Chebyshev inequality. So let x be a random variable with say finite mean, mu, and variance sigma squared, and then for any k positive this thing happen. What is the thing? So I am taking x is a random variable, means it can be both either discrete or continuous. Okay, so for any k positive we have this inequality, probability that mod of x minus mu is greater than equal to k. This probability is upper bound or bounded above by the quantity sigma square by k square. Okay, yeah, so this looks like a simple inequality, but it has lots of applications, not only in probability statistics, in different parts of mathematics also. So let us try to understand geometrically what does mean. So this is a statement, but geometrically what does that mean? So geometrically, so suppose, okay, so I'm telling this thing for a continuous and non-variable, but say similar thing is true for discrete. So suppose we have a continuous and non-variable of like something, okay, and you have some mean somewhere, say here. So suppose this is the mean, this is mu mean, okay, this is the origin 0 0. So this is mean, and then this quantity mod of x minus mu greater than k means the region. Okay, so then this quantity say suppose k, so then this is mu plus k, the full thing is mu plus k, and then this person is mu minus k, okay. So mod of x minus mu greater than equal to k. So what does that mean? That means x is either greater than mu plus k and the union of this quantity. So this quantity and union of x less than mu minus k. Okay, so yes, so what does that mean? So that means either this region or this region. Okay, and Chebyshev inequality tells you that the probability that this region and this region, the total accumulated probability has a upper bound which is sigma square by k square. It cannot be more than that. Okay, and you can also check for For example, Gaussian normal distribution, Gaussian standard normal distribution, mu equal to 0, sigma square equal to 1. It has very nice applications. Okay, so you can easily check with that thing. So that there are many ways to prove this kind of inequalities. So maybe I will start with the classical proof. So obviously this is due to Chebyshev. So proof 1. Okay, so and then obviously there are new proofs also. I will, new means newer than Chebyshev proof. So how to prove? So you start with this variance, which is sigma square, and then you know that variance. Okay, so I'm assuming that x is continuous, but for discrete also you can have the similar proof. So then you can write down this as minus infinity to plus infinity, and you know that x minus mu by definition, and f of x dx. And what is fx? So this is that pdf of x. Okay, so this is by definition. So what does that mean? That means you are taking integration all over minus infinity plus infinity with this. Okay, so you want to find out with the full region what is this value, and that value is sigma square. But what happen if we just restrict this integral over only this region, x minus mu, so greater than k, which we require, right? X minus mu greater than k. Okay, so uh, if you restrict this region, what does that mean? That means you are doing integration either so on this and this portion. So this portion I am not taking, right? So suddenly this integral will be, so the first integral will be bigger than equal to this integral. Okay, because see, in the integrand you have this quantity x minus mu square, that is also non-negative, and definition of PDF tells you that f of x is also non-negative. So this inequality holds. And also now you check that on this region mod of x minus mu greater than equal to k, the minimum value of x minus mu whole square takes, which is k. So we can also write down one more steps here. Okay, so next page, so we can write down that quantity is mod of x minus mu is equal to k is bigger than equal to k square times f of x dx. Okay, so and k is a constant, so you can take out, so this quantity is nothing but k squared times mod of x minus mu greater than equal to k into f of x dx, right? Yeah, so now you can, I hope you can remember what is this integral is. Okay, and this integral is nothing but, so we have this integral is nothing but probability that mod of x minus mu, okay, greater than equal to k. This is the this is this probability, right, by definition. Okay, so mod of x minus mu greater than k, and hence finally you get the result is a result. So the result is what? So probability that mod of x minus mu is greater than equal to k is less than equal to sigma square by k square, right? Okay, and so immediately you have a corollary. So so corollary tells you that, so what about that complement portion? So this portion probability, the probability inside this complement portion, okay, so uh, mu minus mu plus k. Okay, so mu minus k, probably this one. Okay, not this one. Yeah, so this full portion So probability that mod of x minus is that less than k, this is the complementary event, and this probability will be at least 1 minus sigma square by k square. Okay, clear? Okay, and obviously this is a simple version, and there are many versions. Some people also instead of writing sigma square by k square, some people use this symbol k equal to say sigma by c, and if you input k equal to sigma by c, then your statement becomes probability that mod of x minus mu greater than equal to sigma into c, this quantity is less than 1 by c square. Okay, so there are different versions also, and obviously you can study this thing for major theory point of view, other point of view, but because this is the first undergraduate course, so we will give this simple proof. Okay, so this is one proof, and but we can have there are many proofs, so I would like to discuss another important proof, but this proof requires another important identity or inequality, rather say, is called Markov inequality. So let me discuss what is that. What is this Markov's inequality? This is due to another Russian, great Russian mathematician, Markov. And what Markov proof, and how you can use Markov inequality to give a proof of Chebyshev inequality, that I will discuss after this proof. So Markov inequality tells that so let x be a non-negative random variable. So you know what is the meaning of non-negative. It means it takes only a non-negative values. So non-negative random variables, and you choose some say some real number k than 0. Okay, and then what happens? Then probability that x is greater than equal to k, so this quantity is bounded by upper bound by expectation of x divided by k. Okay, so this is a simple inequality, but this will immediately imply the Chebyshev inequality. Okay, so let us first give a proof of Markov inequality. So how do we prove Markov inequality? So proof of Markov's inequality. So k. So what is given? So k positive is given. So we define a new random variable. So I'm defining a new random variable. Say I. So it's kind of called indicator random variable. So what is I? I is 1 if your x is greater than equal to k, and 0 otherwise. So if x is less than k, so this portion. Okay, and also you know that obviously we know that x is what is given. So so I is non-negative. This is clear. I takes only value 0 and 1. Okay, now what is the expectation of I? So now you see that I survive whenever x greater than k greater than equal to k, and the value will be 1. So expectation I is nothing but probability that x is greater than equal to a. So this proof is simple, right? So you just write down expectation of I equal to I mean, so you can, yeah, so that I is continuous, or see, I can be I is taking two values, right, 1 and 2. So I is discrete number variable, but it's supported on this that thing, x greater than equal to b. So you can write down 1 times probability of I equal to I, that is nothing but probability x greater than equal to I, right? So so it doesn't matter whether x is discrete or continuous. You can easily find out expectation of I is this. And so this is observation. Now one more observation, you see that okay, again note that I is satisfying this inequality x over, okay, so sorry, uh, no, so this is k x greater than equal to k, okay. So this I is uh, less than equal to k, because whenever x greater than k, then I equal to 1, and so this quantity is either 1 or bigger than 1, and whenever x less than k, then this quantity I is 0, but x is non-negative, right? So this is always cannot be a negative quantity, so I satisfy this inequality, okay. And then immediately you can write down the expectation of I is nothing but less than equal to expectation of x by k. K is constant, so you can write down 1 by k into expectation of x, okay. Clear? But expectation of I, you have idea, you know that this is nothing but probability x greater than equal to k, okay. This is the expectation of I, and so this quantity is less than equal to expectation of x by k, and this is the proof of Markov inequality, okay. Clear? So the proof is straightforward, and now one can use Markov inequality to prove, to give a proof of Chebyshev inequality. So so let me give the proof. So proof of or rather you can write down second proof, Chebyshev inequality, okay. So now you recall what was Chebyshev inequality. So you have random variables such that mean, mu, finite mean, mu, and variance sigma square. The finite means both this mu and sigma square is finite, okay. Then it tells you that the probability of this outer portion is bounded up by sigma square by k square, and then you can give a proof. So okay, so you start with this random variable x minus mu whole square. Now see that this is a random variable, so so this is a non-negative random variable. So so thus using Markov inequality, so Markov inequality tells me what? So Markov tells me that probability, okay, so so this is non-negative, so I am writing um, probability that x minus mu whole square greater than equal to k square. So okay, so k is a constant, so I am writing k square is that constant, okay. So this is true for any k, right? So for k square also, so this quantity is bounded by expectation of x minus mu whole square by k square, right? This is the Markov inequality tells me. But okay, so there are two things. So first, what is this random variable? So x minus mu whole square greater than k square. So this random variable implies that mod of either x minus mu is greater than equal to k, or x minus uh, so yeah, so let me write down properly. This implies, so this implies that either case 1 x greater than mu plus k, and case 2 uh, x less than mu minus k, right? In both cases, mod of x minus mu whole square is greater than equal to k square. And what does that mean? So this means that nothing but mod of x minus mu is greater than equal to k. Clear? So the left hand side becomes now probability that mod of x minus mu greater than equal to k. Okay, and that is by the identity using Markov identity. We got it, expectation of x minus mu whole square by k square. But the numerator is nothing but the variance, so this is sigma square by k square. Okay, the variance of the distribution. Okay, so you can use different inequality to give the proof of this kind of theorem. Okay, now so there are many applications. So let me give one example or two example first, and then I will show you the other applications. So suppose okay, so this is kind of approximation, right? So how to get a better approximation on that? So that gives you that approximation. Suppose you have x which is uniform random variables, and say uniform 0, 10, and you know that the moment it is given, then you know that expectation is 5 and variance is nothing but 25 by 3. That is already you know. And then Chebyshev inequality tells you that this probability that mod of x minus 5 say greater than 4, so let me write down k equal to 4 here. This quantity is bounded by variance 25 by this by 4 square, means 4 squares, so which is nothing but 25 by 48. Okay, so 25 by 48 means little more than 5 to, okay, something like that. Okay, but you see that, so that tells you that this probability is this upper bound. It cannot be more than that, always less than that. But what is the actual probability? So you can easily find out the actual probability, the exact result is what probability of, and you see this result is 0.2, which is so this value is actually bounded above by 0.52. So yeah, so this is the upper bound. Clear? So you can find out. Okay, so this is one example. Similarly, you can also ask using Markov inequality the example. So another example, say example 2. So suppose that um, the number of items produced in a factory during a week. So in a factory is the number of items. So number of item produced in a factory say has number of item has say mean say so mean is something say 50. Okay, and you want to know that number one, you have to know what is the probability that number of items. So what is the probability that number of item bigger than 75? Okay, and then you can easily, I mean, I want to say that the approximate value, because see here a number variable has mean 50, but we have no idea what kind of number it is, right? So we don't know the distribution of this random variable, but we can give a upper bound of this quantity. We know that using Markov inequality, that tells you that this quantity is bounded by expectation of x, and then divided by this is, if this is k, then this is this, but that this tells you that this cannot be more than that. So what is this quantity? This quantity is something like 2 by 3, right? Okay, so 0.66 approximately. Okay, so the item produced in the factory more than 75 is this probability is maximum 2 by 3, right? Similarly, if you want to use, okay, so this is if you don't know the variance, the Markov inequality, but if you know the variance also, if it is given that the number of item produced in the factory has a mean, uh, okay, so mean already is given 50 and variance um, say 25. Now we can use Chebyshev inequality also, and you would like to know that what is then what is the probability that the weak portion will be in between, what is this probability in between 40 and 60. Okay, so in this case, if you want to apply, so you can easily apply Chebyshev inequality, and that will be the case. So what does that mean? So this you can write down that x minus 50, 50 is the mean, so that quantity is this minus 10, right? And now this is nothing but so what does that mean? So x minus 10, x minus 50 is this and this, so this means this is probability that mod of x minus 50, the mean, is less than okay, so yeah, so the equality doesn't has any problem. Okay, so I'm assuming, and we know that this is 1 minus by that form of Chebyshev inequality, 1 minus variance. So what was the variance? So variance was, okay, so that is bounded above by, not bounded below. So let me show you the form. Yeah, so I'm talking about this one, the corollary. Okay, this is greater than equal to 1 minus this. So 1 minus sigma square, what is sigma? 25. So 25 square is what? So 25 square by k square. So what is k? 100. K is 10, k square means 100. So 100. Okay. So what does that mean? Sigma square by 10 square. So that means, oh sorry, sigma, yeah, no, sigma square is 25. So yeah, I don't, so, oh sorry, not sigma, sigma square is 25. This is sigma square. Okay, so this is greater than equal to 1 minus 1 by 4, which is nothing but 3 by 4. So you can predict that if mean variance is given, you can predict that this probability will be at least 3 by 4. Okay, So this is example. Now let us give theoretical example, and we need to have some theorem first, okay, or you can say lemma. So you can say there are many important formula you can say. So one of those are called weak law of large number. Before that, let me ask a simple question: that what happens, suppose if it is given that variance of a random variable is 0, okay, then this quantity happen, then probability that x is taking the value expectation of x, okay, x is taking the value, the expectation means the mean value, x is taking the mean value, it is 1. So certainly it is a certain event that x takes the mean value 1, okay. So what does that mean? That only random variable having, so this means, so what is the meaning of that? The only random variables having variance is equal to 0 are those that are constant. Constant means they take value, the same value, okay, that are constant with probability 1. So what does that mean? So constant with probability 1. So that means that if it is not constant, that probability is 0 actually. Okay, so I am avoiding the major theoretic point of view. I am giving the simple things. So if the variance is 0, then the random variable must be constant, and it takes values this expectation of this. Now how to prove this kind of statement using Chebyshev inequality? So okay, so so Chebyshev inequality tells you that, so what is this quantity? Mod of x minus mu. So n is some integer, okay, so integer n greater than 1 equal to integer, and then you want to talk about what is mod of this quantity, okay. Now Chebyshev tells you that probability of this quantity, okay, this is bounded by sigma square by, so you remember sigma square by k square. So but sigma, you know that sigma is 0 here, is given variance sigma square, this 0 is given, so this quantity is 0, right? So probability bounded by 0 means what? That means this is actually 0, probability cannot be negative, right? So mod of x minus mu greater than 1 by n, this quantity is 0, okay. Now we recall that we can also think this probability as a continuous function that we discussed long back ago in the class. So we will use that continuity property. So what is this quantity? So I can, so now let me ask you this question first. Okay, so next page. So next page. So what type of random variable is this? So mod of it's not working, pen is not working, so let me, no, I think there is a problem. Now it's working. So x minus mu more of this is random variable, right? So what type of so when you vary n equal to 1, n equal to 2, n equal to 3 and so on, then what type of random variable is this? Okay, so let me give an example. So when n equal to 1, then what happened? Then so the next will then this quantity is nothing but x is greater than mu plus 1 and union is less than mu minus 1, so n equal to 1 case, right? And then when n equal to 2 case will be what? Then it will be x greater than mu plus 2 union x less than mu minus 2. Now you see that this is bigger than this, so this is the kind of this, right? And so on and so on. So this is what, this is decreasing sequence of random variable, right? Now you remember the decreasing sequence of random variables. For decreasing of random variables we define something called the limit by the intersection of this, right? So similarly we can write down the limit of n tends to infinity this random variable which is mod of mu uh, greater than 1 by n. So and this limit is nothing but intersections of over n of these random variables mod of x minus mu greater than 1 by n. And now what is this intersection? So this intersection is nothing but okay, sorry, yeah, this is no, sorry, this is uh, there is a mistake. So n equal to 2, it is 1 by n, so this is 1 by 2 half, this is half, right? So what does that mean? So that means mu minus half, so this is increasing actually, so yeah, it's the other way. So increasing, so this is other way, right? So other way. And for increasing mu plus 1 mu, okay, so this is somewhere mu 1 and then mu minus 1 and then mu plus half, yeah. So this is increasing sequence. And then for increasing, this is union. This portion is the union over n and this, right? But what is the union of this? So you are taking every value except 1. So this is nothing but the random variable that x is everything except that mu. If x is equal to mu, then it will be 0, otherwise, right? So the limit of this will be the random variable x not equal to mu, right? And we know that um, as probability is continuous function, we can prove this property. We can use this property, continuous property, probability of limit n tends to infinity, and then the random variable x minus mu, which is bigger than 1 by n, and this is equal to probability that x not equal to mu. Clear? But this is using continuity property. I know that this is limit of n tends to infinity with probability that mod of x minus mu greater than 1 by n, right? And this quantity is probability x not equal to mu. Clear? Okay, but what is this quantity? Probability mod of x minus mu greater than 1 by n. So this is 0. So already we already noticed this is 0 using Chebyshev. Okay, and so that means the left hand side we have a sequence of 0 values. The limit will be 0. So left hand side this is 0, and hence probability that x not equal to mu equal to 0. Okay, and if x not equal to mu is 0, then this implies that probability that x equal to mu or expectation whatever. So this is the full probability. This is the complementary event, right? So what does that mean? So this implies that if a random variable has variance 0, then it must be a constant random variable. Okay, clear? So this is an important observation. Um, Applications to our Chebyshev inequality. So we will discuss one more application, and this is also very important. It is called uh, the weak law of large number. The weak law of large numbers. Okay, so and there is one more theorem called the strong law of large number that we will define later, discuss later. Okay, so what is the statement? So statement of this theorem is, so we have IIDs x1 x2 dot, dot. So this is IIDs. So what does that mean? Independent and identically distributed random variables. So and they are, because the IIDs they have the same mean, so this means mu. Okay, so this is given. So with this condition, then for any epsilon positive, what happened? Probability that the sample mean, difference between sample mean and the original mean. Okay. So sample mean and original mean. So this one greater than equal to epsilon. This quantity is tends to 0 as n tends to infinity. So so we call sample, what was the sample mean? So this is summation xn over n, right? N equal to 1 to uh, uh, x, rather I can write down xi over n I equal to 1 to n, right? Now when n tends to infinity, this quantity is 0. So what does that mean? That means um, so okay, so let me give a picture of that. So you have mean somewhere mu, okay, and that expected values of this sample mean is mu, already you know that. So this already you know that this quantity x1 xn over n, so this is mu, already proven I think one of my online lecture course, and already we also proved this quantity variance of sample mean. This is already proved. This quantity is sigma square by n. Okay, so so it tells it takes the sample mean and the difference between mean, if it is greater than epsilon, and then it is actually 0. So what does that mean? That means the more you will add this number of random variables xi, and then sample mean is actually equal to the probability, in probability sample mean and the mean are almost same, right? So the difference is greater than, if the difference is greater than epsilon, this probability tends to 0. Okay, so and the proof is simple, because we have the Chebyshev inequality, and that tells you that Chebyshev, so using Chebyshev, so we easily find out that probability that x1 plus xn over n minus mu. So and then so now recall again what was Okay, so yeah, so this quantity is nothing but okay, so this is the mu is the mean, and this is the random, new random variable, which is sample mean. So if it is greater than equal to epsilon, so remember in the theorem it was k. So this quantity is bounded above by variance, which is sigma square by sigma square by n is the variance by k square, which is epsilon square, right? And now you see that when n tends to infinity, then this quantity, see the sigma square is finite and this epsilon is positive quantity. So when n tends to infinity, so this quantity tends to 0, right? So you can make this as small as possible, the full quantity as small as possible, and this is, you can use Archimedean property, right? So this tends to 0. um, you can Archimedean property. So what does that mean? That means this probability that this minus this tends to 0 as n tends to infinity. Okay, so this is called weak law of large number, and this proof is okay. So this is not the original proof. So this proof is due to Russian mathematician named Khinchin. But the originally this theorem is due to, so this proof is due to Khinchin, but because Khinchin used Chebyshev inequality, right? The original proof was due to so let me write down here, James Bernoulli, the same family, Bernoulli family, have lots of mathematicians. I told you in the class, Jacob Bernoulli, Daniel Bernoulli, Edward Bernoulli, all are in the same class. Same Bernoulli, that family. So this is due to James Bernoulli. Okay, the original proof. But we discussed the proof by Russian mathematician Khinchin. Okay, so this is probably I will stop here, but I will discuss about the quiz. For so quiz, in quiz in quiz 3 most of the student has done correctly. Only one or two students sent me wrong answer, rather wrong calculation, but then they said they have misunderstood the problem, right? But anyway, so maybe in quiz 3 we will discuss, give one problem for which you require my last lectures. Okay, so okay, so maybe I can ask this question, this simple question. So so you have standard normal variable or Gaussian distribution with mean 0 and sigma square is 1. Okay, and then obviously you already learned moment join function, so you can use that. So I'm interested to know, so if I'm defining mu n is say that nth raw moment, nth raw moment, okay, and then it has a formula. So formula is the proof that, so that mu n is actually of this form. It is of the form 2k factorial divided by 2 to the power k into k factorial if n is even number of the form 2k. Okay, whenever n is even number of the form 2k, then this is of this form. Okay, and for odd it is 0 if n is odd number. Okay, for odd number it is 0 actually, like the first moment, the mu equal to 0, third moment is 0, fifth moment is 0, but second moment, fourth moment, it has a value, okay, and that of this form. So this simple question, and then solution you send me by today 6th, so 7th, 0420 midnight. Okay, by this you send me the solution, and okay, so maybe I will stop here. And if you have any problem of with today's lecture, if you have any question, anything, comment, you write down in the comment sections. I will reply as soon as possible. Okay, so in this quiz I am interested to know for standard Gaussian distribution, how is this moment look like. So for odd moments of 0, even moments satisfy this nice identity. Okay, so prove this thing. Okay, so thank you for listening carefully, and I will stop my lecture now. Thank you.